In this optional section, what I want to do is revisit the concept of eigenvalues and eigenvectors, in case you've forgotten what they are. They're a concept that we're going to need in the next segment. So let's consider a simple linear algebra case. We have a vector v, it's an n by 1 vector, and we're going to pre-multiply it by a square matrix n by n, and the result will of course be a vector, an n by 1 vector. Now for every matrix A, there are n vectors whose direction is unchanged by A. That means that the vector v and the vector v prime will be parallel to each other. And these vectors we refer to as eigenvectors. Now, although the vector v and the vector v prime will be parallel, they may not necessarily be the same length. So the length is scaled by the eigenvalue that corresponds to the eigenvector. So that's a lot of words. Let's look at a graphical example of this in practice. We've chosen a very simple A matrix. It's a 2 by 2 matrix, so there will be two eigenvectors and eigenvalues. And you can see an eigenvector just about coming up now. That's the case where the red vector, the input vector, and the blue output vector are parallel to one another. There's another one now. Now, notice that they are parallel to each other, but they're not the same length. So the ratio of the length of the red vector to the blue vector is the eigenvalue. So the term eigenvector means, it's a German word, and it means own vector. It's a special vector that belongs to the matrix. So there are a couple of equations that we can write. First of all, we can use the equation that we had before, that V multiplied by the matrix A gives us the output vector V prime. And in the particular case when they're parallel, then they are related by a scalar. The two vectors are parallel, only their length is different. And so we can represent that by the scalar factor lambda, which is an eigenvalue. So if these two equations are true, we can write this. And by following through some maths, we're not interested in the case where v equals 0, we're interested in the case where the determinant of a minus lambda I is equal to 0. So if we can write that expression for any matrix, it's easy for a 2 by 2 case, more difficult for 3 by 3, very, very difficult for bigger matrices. And we can solve that for the values of the eigenvalues, these lambda values. Once we have values for lambda, we can substitute them into the equations above and then solve for the eigenvector. Now, there are an infinite number of eigenvectors corresponding to each eigenvalue, so typically we choose eigenvectors that have got a unit length. That's an additional constraint that helps us choose just a single eigenvector. We'll demonstrate this with a simple example with a 2 by 2 matrix. The eigenvalues of this matrix are given simply using the MATLAB built-in function eig. And we see the two eigenvalues are 1 and negative 2. To find the eigenvectors is a little bit more complex. We have to assign two output arguments from the function eig. And the first output argument, which I've assigned to the matrix X, has got two columns. The first column is the first eigenvector. The second column is the second eigenvector. And the eigenvalues now are arranged along the diagonal of the output matrix E. A fundamental property of the eigenvector is that when it is transformed by the original matrix, it is parallel to itself. Well, let's test that. The original matrix A, and we multiply it by the first eigenvector, which is the first column of the matrix X. And we see that the resulting vector is indeed parallel to the eigenvector. And it has exactly the same magnitude. It's been scaled by 1, and that is the value of the first eigenvalue. So the eigenvector multiplied by the matrix A is a vector parallel to the eigenvector with a scale factor of 1. So it is in fact the original eigenvector. Let's try it with the other eigenvector, which is the second column of the matrix X. And we see now that the result is indeed parallel to the second eigenvector, but it's been scaled by -2, and -2 is the second eigenvalue of the matrix A.